Hey everyone, welcome back to The Explainer. Today we are breaking down a really massive topic in the world of distributed systems. We're talking about rebalancing and hotspots in partitioned databases. Now, I know it is incredibly tempting to think of your database as just this static storage box, right? You set it up, you organize the shelves, and you kind of expect it to just sit there doing its job forever. But if you want to build highly scalable backend systems, you really have to fundamentally shift that mindset. A distributed database is not a static box. It is a dynamic, living system that is constantly shifting and adapting to its environment.
To understand why, picture this scenario. Imagine your engineering team has just deployed this beautiful, perfectly balanced database cluster for a brand new social media platform. Everything is humming along smoothly. Traffic is evenly distributed across all your servers. But then a massive, world-famous celebrity suddenly posts a viral update. The internet goes absolutely wild. Millions of followers start refreshing, liking, and commenting all at the exact same millisecond. So what actually happens to your pristine, perfectly balanced cluster when it gets hit by that massive, unpredictable wave of real-world chaos? Well, things are about to get really messy.
Okay, let's dive into this. Here is our roadmap for unpacking the life of a distributed cluster. First, the myth of static data. Then, we'll look at the anatomy of a hotspot, explore the hashing trade-off, talk about moving data safely, check out some smart rebalancing strategies, and finally, look at why this is a never-ending balancing act. Let's get right to it.
All right, part one, the myth of static data.
You know, we really got to drop this idea that databases are just set-it-and-forget-it blueprints. The reality of software engineering is constant change. Even if your code doesn't change, the world around it absolutely does. Total data volume naturally increases over time. Query traffic and processing loads experience these massive, unpredictable spikes. And let's not forget the harsh physical reality. Hardware inevitably fails. Hard drives crash, power supplies die, and those physical machines have to be replaced. Plus, as your app gets more popular, you're going to need to add brand new machines just to handle the capacity. Because data grows, traffic shifts, and hardware physically breaks, the data partitions in your database literally have to pack their bags and move across different nodes just to survive.
Which brings us to part two, anatomy of a hotspot.
Let's go back to our central social media example, with that massive celebrity account going viral. The crucial point here is defining what actually breaks down in that scenario. Our database is partitioned, meaning the data is split into smaller chunks across multiple machines to share the load. But when that celebrity posts, the traffic doesn't play fair. It all rushes to the specific partition holding that one celebrity's data. This creates what we call a hotspot. It's a partition receiving a disproportionately high volume of read or write traffic. So instead of a nice, shared workload, you get this heavily skewed traffic jam that instantly bottlenecks your performance.
To put that into perspective, just look at how this plays out visually. Look at node A on the left. This server is absolutely sweating through a viral tsunami, pegged at 100% capacity, because it holds the celebrity's partition. Meanwhile, node B and node C are basically taking a coffee break, sitting at a breezy 5% capacity. Your entire multi-million-dollar database cluster is now only moving as fast as that one single overloaded machine. Not ideal, right?
Now, celebrities are just one piece of the puzzle. There are several predictable engineering patterns that can completely ruin an otherwise even distribution of data. Using sequential keys, like writing data ordered by the current timestamp, is a classic mistake. Since time only moves forward, all your current writes will just pile up on whatever partition is handling today. High-profile users, unexpected viral posts, a sudden rush to buy a wildly popular product, or even automated time-based write spikes right at midnight, they can all cause localized database chaos.
Moving on to part three, the hashing trade-off.
So how do we actually fix this skewed data? Well, in system design, there's really no free lunch, right? Every architectural fix has a cost. When figuring out how to distribute data, engineers generally choose between two partitioning strategies. First, you've got range partitioning, which groups similar keys together, kind of like an encyclopedia. It's incredibly efficient if you want to read a continuous sequence of data, but as we just saw, it is highly prone to massive hotspots. To counter this, engineers often use hash partitioning. By running the key through a mathematical hash function, the data gets scattered uniformly across the cluster. This is fantastic for reducing hotspots, but here's the trade-off. Because the data is now randomly scattered everywhere, your ability to easily execute sequential range queries is effectively ruined. It's a classic engineering compromise.
But wait, there is a huge catch here. Hashing is awesome for distributing a million normal users, but hashing literally cannot fix a single viral key. Even the most sophisticated hash algorithm in the world will output the exact same result for that one celebrity's user ID.
which means all millions of likes still go to the exact same partition. In these extreme cases, engineers actually have to go in and manually append a random 2-digit decimal suffix to the celebrity's key. This manual splitting trick forces the single viral key to act like 100 different keys, successfully forcing all that crazy traffic to spread across multiple nodes.
Okay, so let's say we used our hashing and our clever splitting tricks, and our cluster successfully survived the viral post. Phew! But now the business is growing fast, and we need permanent, scalable capacity. We need to add a brand new server to the cluster. The million-dollar question is, how on earth do we do that without breaking the whole system?
That leads us right into part 4, moving data safely.
We've got to move some data from our old machines to the new machine. This introduces us to the concept of rebalancing. Rebalancing is the process of moving data and request responsibilities between nodes to keep the load even. And let me tell you, delicate is the key word in this definition. If you don't engineer this process with incredible precision, you can accidentally take down your entire production database. So, to pull this off without causing a 3 a.m. PagerDuty nightmare, systems have to follow 3 non-negotiable golden rules. First up, fairness. After the move is done, the workload absolutely must be shared equally. Second, availability. The database has to stay online and keep accepting reads and writes while gigabytes of data are moving in the background. And third, efficiency. You must never move more data than is absolutely necessary over the network. Network bandwidth and disk I/O are precious, you know? Wasting them on unnecessary data movement will just stall out all your other queries. And because of that third rule, efficiency, simple math totally fails us here. You might think, hey, why not just use a simple modulo operation? Like if you have 10 nodes, you take the hash, divide by 10, and the remainder is the node number. Simple enough, right? But hash modulo n is actually disastrous. If you add just one new server, your total node count becomes 11. Now you're dividing every single hash by 11 instead of 10. The math changes for almost every key in your database. You would end up having to shuffle almost all your data across the network to entirely new servers, completely violating the golden rule of minimizing data movement. Total disaster.
So what's the actual fix? Let's hit part 5, smart rebalancing strategies.
Instead of naive math, we use smart architecture. Take dynamic partitioning, for example. I love this one because it behaves almost like a biological cell dividing. First, a partition slowly fills up with user data. Second, it crosses a configured maximum threshold, say 10 gigabytes. Third, the database automatically steps in and splits that partition perfectly right down the middle. Finally, to relieve the pressure, one of those new halves is transferred over to a brand new idle node in the cluster. Boom! The load is instantly halved and everything keeps humming along smoothly. Now, dynamic partitioning is super clever, but it's not the only game in town. Let's briefly contrast the 3 major strategies modern NoSQL systems use to maintain equilibrium. First, fixed partitions. This is where you create way more partitions than you have nodes, like 1,000 partitions for just 10 nodes. It's very stable, but guessing the perfect size up front is tricky. Then there's dynamic partitions, which we just saw. It splits and merges based on size, but an empty database starts with just one partition, which creates a temporary bottleneck at first. Finally, making partitions proportional to nodes keeps partition sizes stable as you scale hardware, but it relies heavily on randomized hashing to keep things fair.
But regardless of which strategy your database uses under the hood, you have a huge operational choice to make: automatic versus manual rebalancing. Fully automatic rebalancing sounds great, right? Very convenient. The system sees an imbalance and just fixes it. But it's actually really dangerous. If a node is just having a temporary network hiccup, the automated system might panic, think the node is dead, and start migrating terabytes of data around. That overloads the network and causes a massive cascading failure. And that is exactly why keeping a human in the loop with manual rebalancing, where the system suggests a plan but an operator has to click approve, is often much, much safer. It significantly reduces those terrifying operational surprises.
And finally, part 6, a never-ending balancing act.
Look, if you only take one thing away from this entire explainer, let it be this. Partitioning your data is not just some one-time architectural decision you sketch out on a whiteboard and forget about. Distributed systems are highly dynamic, living organisms. They require ongoing, continuous balancing. Your users are going to behave unpredictably, your data volumes will surge, your physical hardware will degrade, die, and need replacing. Rebalancing is literally the heartbeat that keeps the whole system alive. So, I'll leave you with this final, crucial question to ponder. As your own applications start to really scale up and that traffic comes pouring in, is your partitioning strategy actually ready for the unpredictable chaos of the real world?
It's something every back-end engineer has to face eventually. Thanks so much for hanging out with me for this explainer, and keep building resilient systems.